Well, students, so last time we had seen some failures of Rutherford, right? So Rutherford failed mainly due to the reason that he could not explain when electrons revolve around a circular orbit. So Maxwell said it has to radiate electromagnetic radiation. But Rutherford could not explain why it was not liberating, or the emission of electromagnetic radiation was not explained by Rutherford. So next comes the man, the Bohr. Okay, so Niels Bohr, he comes with an idea that how you can overcome the Rutherford's failures. Okay, the first one, what he says, electrons revolves around the nucleus in an atom in a circular orbit, and he says the necessary centripetal force, okay, centripetal force is provided by the electrostatic force of attraction between nucleus and electron and nucleus. So it was already been explained by Rutherford himself, right? So Rutherford also said the same thing, that the centripetal force is provided by the force of attraction between electron and nucleus. Now comes the main explanation how electrons are not liberating energy when they revolve around circular path. Okay, electron can revolve only in those circular orbits. See, only in those circular orbits in which its angular momentum, see this, electron can revolve around only on certain orbits in which angular momentum is integral multiple of h by 2 pi. So electron doesn't revolve around any continuous orbit, right? It is not everywhere. It revolves around in a certain orbits where its angular momentum is integral multiple of h by 2 pi. So where this h, it is nothing but Planck's constant. Okay, it has got a value 6.626 into 10 to the power minus 34 meter square kg divided by second. Okay, so this is nothing but a very important concept which changed the entire idea of physics. Okay, it was given by Planck, Max Planck. Okay, so you can see here, what is this? Angular momentum, mvr, that is equal to integral multiple of h by 2 pi, where n is nothing but, it is an integer, it can be 1 or 2 or 3, which is known as principal quantum number. Okay, you already came across this in your chemistry. Okay, so it says that, listen carefully, electron can revolve only in those orbits in which its angular momentum is integral multiple of h by 2 pi. Okay, so mvr, angular momentum, is nothing but n into h by 2 pi. Okay, now electron can revolve in certain orbits of definite radii. Those orbits are called stationary orbits. So electron doesn't, see, I have already explained you, electron won't revolve everywhere. So they revolve in certain orbits. Okay, and each orbit has got certain radius. So those orbits are known as stationary orbits or stable orbits. When electrons revolve around in these orbits, stationary orbits, they don't liberate or they don't give out energy. They move in a stable manner. Okay, in stationary orbits, electrons do not radiate energy in spite of their circular motion towards the center of the nucleus. Correct, right? That was a failure of Rutherford. He couldn't explain why when electrons are accelerating continuously in a circular path and they are not liberating energy. So that was proved, or that was okay. The explanation was given by Niels Bohr, saying that they revolve around stationary orbits. Okay. Next point, electrons radiate energy only when they jump from higher energy orbit to lower energy orbit. See this, you can see nucleus over here. See this, lower energy orbits, higher energy orbit, again higher energy orbit. So electron will liberate energy only when they come from higher energy orbit to lower energy orbit. So how do they go to higher energy orbit? If these electrons to be excited to the higher energy orbit, you need to supply energy. When you supply energy, electrons will jump from lower energy state to higher energy state. So this energy may be in the form of heat or any sound or light, whatever it may be, any form of energy, electrical energy. So any form of energy you can use. So when you apply this energy to the atom, what happens? Electrons will get excited to the higher energy orbit. When they come back, they liberate equal amount of energy what they have absorbed. Okay, so they will liberate the amount of energy what they have absorbed. Why? Because these electrons which belong to the first orbit will not be stable in the second orbit. Okay, and meanwhile there is no position for the electron. If they get this much of energy, then only they will get excited to the higher energy. Okay, otherwise the energy will be liberated in the form of thermal energy. Okay, heat energy. So you can see this equation. It is a energy in the second orbit minus energy in the first orbit. It will be, the energy difference will be in the form of h nu, where h is nothing but the same Planck's constant what you have seen there. Nu is nothing but frequency. So you know this formula, E is equal to h nu, or also you can write E is equal to hc by lambda. This is another equation given by Planck. Okay, so next one, it is an important 3-mark question. There is a chance that it will be asked for your exam. Equation for radii of both stationary orbits. So how you can find out the value of radii? So we have an equation for that. We will derive that equation. So before deriving the equation, we will consider some of the things. You can see here, Ze charge of electron, and I'll take E as charge of, Ze is nothing but charge of nucleus, and E is charge of electron, and M is mass of electron, R is the radius of orbit. Okay. While considering these terms, we can prove an equation, or we can derive an equation for the radius of first orbits. Okay, radius of the orbits. For that, what we are considering here is nothing but centripetal force is provided by the electrostatic force of attraction. The same postulates given by Bohr has to be considered over here. Then we can write mvn square divided by Rn. You know, right? Centripetal force. That is equal to 1 by 4 pi epsilon naught Ze square divided by Rn square. Okay? It is your first formula, Coulomb's law. The formula what you have derived from Coulomb formula, right? Coulomb's equation. Now, what you can do, you can cancel R and R over here. Now you are getting an equation. See here, mvn square is equal to 1 by 4 pi epsilon naught Ze square divided by Rn. Okay, where n is nothing but 1, 2, 3, etc. It is an integer. So according to Bohr's postulate, we have there mvn Rn, that is equal to n h by 2 pi, integral multiple of h by 2 pi, which is this angular momentum. Correct, right? Okay, so let me consider it as equation 2. Now what I am going to do is, I'll square equation 2. Squaring means m square, vn square, Rn square, then on the right hand side n square, h square divided by 2 pi square. 2 pi will become 4 pi square. Okay. So you can see here, equation, you have to do some cancellation over here. M square has to be cancelled with the m. See, you will remain with the m. After that, vn square cancel. Rn square cancels with the Rn on the right hand side. Just be careful. Then you can see here, 4 pi will get cancelled with the 4 pi on the denominator. What is remaining over here? You have m over here, Rn, then on the right hand side, you have epsilon naught, h square, then n square. Here, denominator pi, then e square and z. Okay. I'll take m to the right hand side, so you can get equation for Rn. What is this? Rn is equal to epsilon naught h square divided by pi into m e square, and the bracket we are taking it n square divided by z, because it's a constant. See, all these terms are constant, right? It will have a fixed value for every orbit, but these values might vary for different. See, if you consider this at z, what is it? Atomic number, it might vary, and n orbit, so that also might vary. So that's the reason why we are taking it as a separate term. Okay. You can see from this equation relation between Rn, okay, and n. See how Rn varies with n. It is square, correct, right? So if I give the value as n is equal to 1, okay, what happens over here? Rn will be 1. If I give n is equal to 2, again Rn will be equal to 4. If I give n is equal to 3, Rn will be equal to 9, right? See, look at the way the distance between the nucleus and the orbit varies. Okay, stationary orbits are spaced in the ratio 1:4:9. See, it is not spaced continuously. You can see the gap. See, first orbits will be over here, second will be a bit far away from the first orbit, again far away from the second orbit, we will have third orbit. So it is in the ratio 1:2. So if, sorry, not 1:2, it will be in the ratio of square. Rn is proportional to n square. Okay. Now if I give the value for Z and n, okay, I am considering hydrogen. So hydrogen has got atomic number 1 and it has got only one orbit, right? So if I substitute the value over here for this equation, Rn is equal to, so n is 1, R1 is equal to epsilon naught h square divided by pi m e square into 1 square. Why? It is 1 by 1 over here. Let me take it as 1 square. So it doesn't have any meaning. Okay, for the value will be the same, so we will discard it. And after doing the calculation for these things, okay, by substituting values for this, what we are going to get is nothing but 0.53 into 10 to the power minus 10 meter. Okay, what is this 10 to the power minus 10 meter? We will consider it as Armstrong. So the radius of the first orbit of hydrogen atom is nothing but 0.53 Armstrong. Okay, so look at the value 0.53 Armstrong in terms of 10 to the power minus 10. So it's a very small value, right? So this value is always like known as Bohr's radius and it is denoted by small letter a naught. Okay.